Hi, welcome to lecture 23. In this lecture, we're going to go through a number of examples that involve momentum, momentum conservation, and impulse. And in this lecture, we're going to stick to examples where collisions happen in 1D. And in the next lecture, we're going to go to 2 and technically, any number of dimensions. So the examples I've listed here that we're going to go through, we're going to have 2 train cars crash, where one moving object hits a stationary one. And then, maybe one comes to rest or maybe even bounces back. We'll see how all that works. Practice, we're going to have an arrow hit a wooden block and they stick together. And we've got 2 ice skaters explode. That's a technical term. It doesn't mean they're literally blowing to pieces. It means that they sort of move apart while starting together. We're going to have a rocket engine and see how we can apply it. We'll learn about impulse and its relation to momentum and changing momentum. And finally, we're going to look at a fire hose where we'll essentially have continuous collision where there's constantly water coming out, hitting a target. And what force do we get from there applying what we learned about momentum to this example. Okay, so let's get started. And here's my first example. I imagine I've got 2 train cars. I'm call them A and B. And A moves with 4 meters per second towards B. We're going to consider 2 cases. One where the car A comes to rest, and the case 2 where the car A actually bounces back. Notice that this one's 12 tons. This one I've loaded up with stuff, so it's 24 tons. Okay, so let's do case 1. And all we have to do here is apply momentum conservation. So we're going to write down the total momentum before. Of course, if it's been a while since you watched the introductory lecture on momentum, then now is a good time to actually pause this and go back, because I'm not going to re-explain momentum conservation. We're just going to apply it and see how it works in practice. So there's total momentum before the collision, and that is equal to, well, 12 tons times 4 meters per second, plus, what about this one, 24 tons, but it doesn't contribute at all, right, because it has 0 initial velocity. So that comes to 12 times 4, it's 48 ton meters per second. Now you might be like, should I convert this to kilograms? You could, however, because the train cars are still going to be in tons afterwards, I'm not going to use any other units other than what you see here. I can just keep everything in tons. Right, there's no newtons or anything else that sort of secretly involves kilograms. So as long as I keep everything consistent, I can work in tons, and my units are not ton meters per second. Total momentum afterwards. So after the collision, this is case 1, right? So case car A bashes into this one, comes to rest, but car B is going to move off. It's going to be 12 tons times 0. Right, that's what we are told. We're told because it's case 1, car A comes to rest after the collision. Right? So A at rest now. Then I add to that the momentum of the second one. I don't know what it is. I don't know what its velocity is. Let's give it a name. Let's call it U. I've used V up here, so I'm going to use U. It's kind of a strange physicsy thing that physicists like to, when they've used one variable already, sometimes we just sort of go to one that's next to it in the alphabet. It's a little bit strange. V velocity, okay, V is used, let's use something else. Okay, let's go with U. So what is this? Well, I don't know what this is, but I know that this one and this one, well, I can write out what the total is. If this is 0, 24 tons times U, I know that this one and this one, they're equal. Right, those two are equal. Why? Momentum conservation. Right. So I have that 48 ton meters per second is equal to 24 tons times U. Easily solve that, and we find that U is 2 meters per second. Right, so course, we can almost do this with on a glance. Okay, 12 times 4 is 24 times what? Right, but the only reason you can do it that fast is because this one is at rest initially, this one is at rest in the end, in the case of case 1. Let's go to case 2. So in case 2, the initial momentum, that hasn't changed. The initial situation is exactly the same. So the initial total momentum is still what we found down here, right? That calculation, the calculation here hasn't changed at all. We're still at 48 ton meters per second. But now let's assume that car A, it bashes in and it bounces back. Let me draw this very quickly. So I'm going to, so after the collision, here are my train cars, very quick sketch, right? It just collided. This is done with stuff on top. This one is now going backwards at 0.5 meters per second. That was our assumption. So how fast is this one going? Let's call it, call the first one U. I guess we're going to go, I'm going to call this U subscript 2 because it's case 2. Could have called the first one U subscript 1. But I'm not going back now to change it. So what we have here in our final total momentum, is going to be the momentum of this plus the momentum of this, right? Not individually. Their sum is what's equal to this one. So what is that? 0.5 meters per second times 12 tons, that's this one here, plus 24 tons, 24 tons times U2. That's not quite right. Why is it not quite right? Let's just say 24 here. Because this one's going backwards, right? And by saying that the initial momentum when the car was going to the right is positive, it implies this one is negative, so you have a minus sign here. Right, it's going in the opposite direction. So that means, well, I'm going to have, I can simplify it a little bit, minus 6 ton meters per second plus 24 tons times U. And now that is equal to 48, right? This is my total momentum. So I've got, by momentum conservation, by momentum conservation, at 48 ton meters per second, the initial momentum at the beginning, the initial total momentum, is equal to minus 6 ton meters per second plus 24 tons times U. I can just simplify it, take the 6 to the other side, I get 54 ton meters per second is equal to 24 tons times U, and I can solve this for U. Not mistaken, that makes 2.25 meters per second. Okay, that's my answer to this. One thing to note here is generally the case when you know everything that happens at the beginning, right? So before the collision, we knew all the velocities at rest, all the mass, everything is known. That alone does not determine what happens afterwards. There are different possibilities. This one might come to rest, this one might shoot off, they might stick together and roll together. This one might bounce back with a certain speed or then some other velocity. Of course, there are factors that are going to determine what actually happens, but momentum conservation alone is not going to completely solve what happens afterwards, right? You need some other input, like in this case, our input was, okay, we know car A comes to rest, or car A rebounds at 0.5 meters per second. Or the two stick together. Whatever the condition is, there's some additional piece of information we do need every time. Alright, let's go to the next example. Here's the next example. I imagine an arrow hits a block of wood that's sitting on a table right here, and the arrow is 30 grams, the piece of wood is 600 grams, and the arrow moves at 42 meters per second. I think those are fairly realistic values. And now the arrow gets stuck. Right, the arrow gets stuck. So afterwards, they're going to move together. So let me just draw this over here, little drawing. Right afterwards, I've got my piece of wood here. and my arrow is nicely, deeply stuck inside it, and they're going to move together at some unknown velocity. Let me call it v final. It's the final velocity. Final meaning at the end of the collision. So I'm naming my things differently every time just because I can, right? It doesn't matter what you call things. It doesn't matter whether I use u or v or anything else. You make your own choices. Just try to be consistent and try to name your variable something that makes it easy to understand what's going on. Okay, so let's use momentum conservation. So total initial momentum. Again, you want to all the components. So it's going to be grams. So everything here is in grams. So I'm going to stick with grams, right? Same thing we stuck with tons the first time around. Yes, kilograms is the standard unit, but as long as I'm consistent, I can work in grams too. So initial momentum is going to be 30 grams times 42 meters per second plus 600 grams times 0 meters per second. So this one just drops out, doesn't do anything, and then that leaves me with 1,260 gram meters per second, or 1.26 kilogram meters per second. Okay, total initial momentum, we worked it out. Now afterwards, what's happened afterwards? They're both moving together, they're moving at the same speed. Right? That's a bit like the example with the truck and the car that we worked through in the previous lecture. So the total final momentum that's equal to, well, what's the total mass? The total mass is 600 grams, it's the block, plus 30 grams. Right, they're moving together, they're now one object. Moving at an unknown speed v final. Always momentum, mass, times velocity. And everything is in a positive direction. Now, of course, mathematically you might find if this is a negative number that tells you that the thing is going backwards. But I think we anticipate, look, the momentum is to the right. It's going to continue to move to the right. So that is 630 grams times v final. And so now again, I said those two equal to each other, right? Those two are equal. So though these two values are equal, I'm not taking the initial momentum of the arrow and say it's equal to the final momentum of the block or something like that. I always consider the sum of all the momenta. In this case here, this one was 0, this one was something, so the something was the total, and now afterwards everything is moving, so I've got a total mass to worry about. And they're moving at the same speed, which is why I was able to combine them, because they're stuck together. So I've got 1260 gram meters per second is equal to 630 grams times v final. You can see the grams are just fine, I can cancel them out. If I'd worked in kilograms, well, I just put 1.26 and 0.63 is the factor of 1,000 on both sides. It doesn't change any of the algebra really. Of course, that easily is, they're nice numbers. Of course, they were chosen to work out nicely. Exactly 2 meters per second. And that's the instant after the arrow hits. You can imagine that if I then wait a second, friction with the table will have slowed this down or it falls off, like other things will happen, right? So this is really right after this collision is finished and the arrow and the block have stopped acting forces on each other. Here's this next example. Of course, we could have a question where maybe you're told this piece of information and you have to find out how fast is the arrow moving. You set it up exactly the same way, except then this one would be not known and this one would be known here, but you just solve for a different variable. Right? So don't necessarily always have to solve for what's the end result. Sometimes you know the end result and you ask what happened first. Say you know two cars crash and you see them slide at a certain speed. You ask, well, how fast were the cars going beforehand? Who was speeding? Right, and that's the kind of example you might do that. Right, let's go to the next example. So here we have two ice skaters and they're going to explode. And an explosion is a technical term that essentially means you put objects that are sticking together. They might be at rest, like here, or they might be moving. And then something happens and now they move apart. That is what we mean by an explosion in the context of mechanics. It does not mean that anything is actually to be literally blowing up, right? No blood and gore in this. Alright, so what do we have? Those two are at rest. And afterwards, this is my before, I mean, actually label those. This is the before situation, this is the after. Think of it as a collision. Explosion is a type of collision. It's a short-lived interaction. That's how we defined what a collision is. Sorry, what a collision is. So go back to the previous end of the previous lecture to review that. So what's my initial momentum? Initial, I should say, total momentum. It's always total that matters. Well, that's just going to be 0 because everybody's at rest. 60 times 0, 80 times 0. So how can anything be moving? How can I end up with like any motion at all if the initial momentum is 0? There's no momentum to go around. Here it's important to remember that momentum is a vector. Right? Momentum does not act like a sort of like a cake where you get a piece, you get two pieces, you get a large piece, I get a small piece, right? And then it's all gone. That is not how momentum works. It's a vector, so values can be negative. So what that tells me then is that if one of them goes left, one of them goes right, they must have the same magnitude of momentum, it's just one of them is negative because they're going left, or whichever direction I call the negative one. So the final momentum, this is the final speed we want to know. Let's call this v. Why not? So I have the two masses. This one was 60 kilograms. This skater was 80 kilograms. Right? We're told over here. So I've got the final total momentum. It's equal to 60 kilograms times, okay, which direction is positive? Let's make left positive. Why not? We can do that. Where can I write this? Right, like here. Plus VE positive. Right, left is positive, just for a change. We don't get too set in our ways. So this one has a positive velocity, 2.4 meters per second. This one is an unknown velocity v. So I'm going to use v to literally just label the velocity, not the speed. So plus 80 kilograms times v, the unknown v. Okay, so those two, right, once again, those two are going to be equal to each other. That is momentum conservation. The total momentum is conserved. So how can it be? Well, I've got 0 equal to 60 times 2.4 plus 80 kilograms. Should keep my units. Times v. So I can rearrange this. When I get minus 60 kilograms times 2.4 meters per second, that's equal to 80 kilograms times v. And now I can just solve this. And you should find very straightforwardly, divide both sides by 80. Actually multiply this out. We find that v is going to be minus, because there's a minus sign here, 1.8 meters per second. So make sure you can go from this line to this line, right? This is not a mystery to you. If you don't see this, you can give me the answer 1.8, right? Make sure you understand how to finish this. Be fairly straightforward. So how do we interpret this? Well, this is my speed, right? And in this case, the minus sign means we're going to the right. Because we said to the left is the positive. Now, had we made a different choice, and if we'd made a choice that to the right is the positive direction in our coordinate system, then this value here would have been negative. I would have had minus 2.4 right here. Then I wouldn't have the minus there when I take it the other side. And so my answer would have been plus 1.8 meters per second. But of course, plus 1.8 in that case, because to the right is positive then, would have been motion in the same direction at the same speed. So the physical answer is the same, it's just expressed in a different coordinate system. Alright, let's keep going. Now we come to a problem that we can solve using the concept of impulse. Right? And so impulse was the force that's acting times the time over which it acts, and that was equal to the change in momentum p. Of course, I should really use a vector here. I mentioned I've got a rocket. It's 2,000 kilograms for a fairly small rocket, and then there's a thrust at 60,000 newtons. I want to figure out what is the speed of the rocket after 10 seconds. Now, the first thing I want to say is you can solve this just by using Newton's laws. Right, just use Newton's laws. Newton's second law, F equals ma, figure out what are the forces acting. Gotta do that anyway. And you know, work it out. Work out the acceleration. From acceleration, you can find the speed after 10 seconds. So change in speed. Because you know how to do kinematics. So you can do that. There's nothing to stop you from doing that. We're going to solve it using this, and of course this is just a rewritten version of Newton's second law. Right? So there's no mystery why those two ways of solving it are pretty much equivalent. Okay, so the force is 60,000 newtons, and that gives me a change in momentum. A change in momentum, in this case here, because the mass of the rocket is constant, at least for our purposes. Yes, it's technically losing fuel, but that's a more complicated problem that we can talk about in class. It's called the rocket problem. The change in momentum is just the mass times the change in the velocity, because this is really just a constant. So what do I plug in here? Well, my time I care about is 10 seconds. Right? But what do I put in for the force? Do I put in 60,000 newtons? Well, that's the thrust. It won't give me the right answer because there's another force acting. That's gravity. Assume the rocket is taking off, presumably from Earth. So here I've got really what I should be putting in here is the impulse imparted by all the forces. Let me write this out then. So F thrust times delta T plus the force of gravity, the weight, times delta T, that. All those forces, there are no other forces. I'm ignoring air resistance. It's up in the air. There are no normal forces, no tensions, no strings attached, right? Those are the only two forces acting. That is equal to m delta v. Okay, and now I can plug in the actual values. You have to be careful because the thrust is up, gravity is down, right? So one of them is going to be negative. We have to pick which direction we call positive. I'm going to make the upwards direction my positive direction. I'm going to make a note it down here so I don't get confused. So 60,000 thrust, that is positive because it pushes the rocket up. Even though the hot gas gets pushed down, but that's not what I care about. I care about what is the force on the rocket. 60,000 newtons times 10 seconds plus the force of gravity. The force of gravity is, of course, minus mg. It's minus because gravity acts down, but upwards is positive. So it's going to be minus, what's the mass? Oh, 2,000. We wrote it right here. Times g, 10. Or 9.8, right? Let me just annotate this as g. Times 10 seconds equals the mass, 2,000 kilograms, times the unknown change in velocity. Notice I don't know what my initial velocity is. The rocket's already taking off. It might be going, 50 meters per second right now. But I don't need to know. I only want to figure out what's the change. But for the final velocity, yes, I need to know where did I start at the beginning of those 10 seconds. Otherwise, I can't say where I ended at the end of the 10 seconds. But no matter what those values are, I can figure out what's the change in the velocity using this. And that's exactly the same thing if you were working with Newton's laws and acceleration. Let's plug in the numbers. This is going to be 600,000 Newton seconds, and this is going to be minus, this is going to be, sorry, this is right. So this is, yeah, this is going to be 200,000, 200 times 10 times 10. Sorry, I just didn't see one of the tens and I got confused. So that seems odd. Here, the units are kilogram meters per second squared, but then times seconds, so it's this. Notice that those two are actually the same units, because Newton is kilogram meter per second squared, and then multiplied by seconds, and it cancels out this one with this one, and it's the same unit. So a Newton second is the same as kilogram meter per second. And that's going to be the 2000 kilograms times the unknown change in the velocity. Well, we can solve this. This is 400,000 kilogram meters per second equal to 2000 kilograms times delta V, and if I'm not mistaken, that makes delta V equal to 200 meters per second. Plus 200, right? I've kept track of signs. Good. If this had been bigger or this had been smaller, it might have been negative. But now it ends up being positive, so we're gaining upwards velocity because upwards is positive. Right? We're gaining speed in the upwards direction, 200 meters per second. Okay. Hopefully it makes sense. And again, I encourage you to work through the same example, but using Newton's second law, so you can see kind of how the calculation is analogous. Now, let's suppose, stick with our rocket. Oh no, we're running out of fuel. And so this is what happens to our thrusters. Our thrusters produce 60,000 newtons, but then running out of fuel, the thrust decreases, they stop burning after 20 seconds. 20 seconds later, oh no, they've stopped altogether. Don't put out any more force. Okay, so how would I find the impulse imparted by the thrusters during those 20 seconds? Impulse due to thrusters. Of course, if I want to know what happened to the rocket, I also need to take into account gravity, if it's still close to Earth. Thrusters during these 20 seconds. And that's what we want to find. Now, I can't just say force times time, because, well, you know, say here it's second 17, the force is not 60,000 newtons, it's whatever it is. So that means how do I deal with that situation? And the way we deal with it is like this. We're saying, okay, F delta T applies if F constant, right, during the time delta T. So we had a similar situation before where we were calculating distance traveled and we had speed times time, or velocity times time. So mathematically, it's kind of analogous to that. So we'll do the same thing we did back then, which is that we say, okay, well, if my thrust changes, my force changes, I just imagine I'm going to split my my time interval into lots of tiny time intervals. And so I like go for 1 second we're having 60,000. For another second we're having 57,000. The next second we're having 54,000, and so on. And if I want to be more exact, I can make my time intervals smaller. I make them 0.1 second, 0.0001 seconds. Do the calculation. Find the impulse during each of those tiny intervals using this, then add them up. One thing to note, of course, is again, by analogy with velocity times time giving distance, you see that force times time is the area under the graph. When I say under the graph, you of course know what I mean. Between the axis and the graph. This generalizes to non-constant forces. Right? By that logic, I can say, well, for this first fraction of a second, force times small time interval equals the area. During the second small time interval, again the same is true because I build up my area using rectangles. But then the total impulse is just the total area because I've added up little areas. Exactly the same logic we had when figuring out that the area under the velocity time graph is the distance traveled. So look back to that lecture in kinematics if you don't remember how the logic here goes. But really what we're doing is we're building up integration. We're doing what's called a Riemann sums. And so if I wanted to include this explicitly, I could. I don't want to do it geometrically. Like here I can do it geometrically. Half times base times height will give me the answer. But I can also write down mathematically. So impulse is equal to, well, the sum of lots of force times tiny time intervals. That is what we mean by an integral. I can write as an integral between the start time and the end time, because that's where our summing starts, here, where it ends. This is mathematically how you'd write that down. So if you understand integrals, you can do any problem, any function that's a force, where you know the force against time, you can solve it. In our case, here we can do it geometrically. The triangle, the impulse J, it's often written as J, is 1/2 times 20 seconds times the height, 60,000 newtons, which comes to 600,000 newton seconds. Half times 20 is 10, 10 times 60,000, 600,000 newton seconds. During those 20 seconds. Okay. And of course now I can give you any other shape of graph and you can figure out what is the impulse during the time. That's another final example. So here's the final example that I want to look at. I imagine there is a fire hose and there are 3 firemen and women holding this, and they're spraying water against, let's say there's some kind of board here, maybe for target practice, where they're shooting the water stream against. And I don't really care about air resistance, it might slow down the water, or gravity. I'm just saying if the water comes out, they're fairly close to it, they're just going to hit it right there. And let's say 20 liters of water come out of this every second. So it's 20 kilograms of water per second. Or something like a little bit more than 5 gallons if you're the imperial unit type. So, and we mentioned the water emerges at 50 meters per second. I think those values are sort of realistic-ish for real fire hoses, at least in the right kind of range. I want to figure out what is the force against that board. Like, are they going to knock it over? Like, how sturdy does it have to be? What is the force against this board? So here's how I would think about this. I ask her, this is a collision, like it's continuously colliding. So what's the momentum, change momentum of the water every second? So I would do this by consider 1 second. In that case, I have a mass of 20 kilograms and the velocity is 50 meters per second. Right. So I'm going to use impulse. Well, the water hits the board and then just sort of drips down, so its final velocity is 0. The delta V of the water is equal to 50 meters per second. Right, actually it's minus 50, we go from 50 down to 0 when we hit the board. And I assume this is my positive direction. So that means the change in momentum per second of the water, well, it's just going to be 20 kilograms times minus 50 meters per second, which comes to exactly minus 1000 kilogram meters per second. Okay, so but that's a change in momentum. What's the force then? Well, that is equal to the impulse due to the board on the water, because the board stopped the water. We call it the target board. Notice, as a side note, as I'm working through my problem, like half the time I write equals and then I write something in words, right? I don't just sort of do algebra and get lost in my numbers. I always write, what am I doing? What am I setting equal to what? What's going on here? Right, we're doing physics. So half my equations are really spelled out in words, and so I know always what's going on. It's not a good sort of practice as you're doing problems. The impulse to the target board, the impulse on the water due to the target board, so of course then the force times the time. Well, what's the time? Well, we were saying we're considering what happens in 1 second. Now we could have worried about what happens in 2 seconds. Then of course I would have doubled the mass, and I would have 2 seconds here, and the final result for the force would be the same. So here I've got F times 1 second. And so I can set those equal, right? Change momentum is equal to the impulse. So I'm having minus 1000 kilogram meters per second equal to the unknown force times 1 second. Well, that's easy. That makes the force due to the board on the water, and conversely of the water on the board by Newton's third law, it's the same both directions, that is going to be minus 1000 kilogram meters per second squared. When I divide by 1 second, I get a second per second squared over here. So that is 1000 newtons. It's minus 1000 newtons, but notice I worked out the force on the water due to the board. So on the water due to the board, that's the board's pushing the water to the left, right? Because it hits it and stops the water. Conversely then, the force on the board due to the water is 1000 newtons to the right. How much is 1000 newtons? Well, that's like holding up 100 kilograms, which is, you know, I mean, if you lift 300 kilograms is an awful lot. 220 pounds. Like if you get hit by this, it's like you get sort of crushed by 220 pound weight on you. And so, you know, when certain, I guess certain, you know, political regimes like to use this against protesters, you hose them, and it hurts. It hurts because it's a really big force. So people can get injured when they get hit with streams of water, say when it's used to oppress protests, for example. All right. But this is the force. This is how you do it. This is a continuous collision, right? It keeps happening, but we analyze it by saying, okay, what's happening in 1 second or 1 minute or whatever is a suitable unit. Okay, so I hope those examples helped a bit. In the next video, we're going to talk about, and we're going to be looking at some examples of collisions in more than 1 dimension. So I'll see you there.